Moving on to the next section here of Chapter 11, cover valence bond theory. So again, this is partially true, not totally true. This energy diagram is true. So y-axis is energy, um, x-axis is the internuclear distance between two hydrogen atoms, and you have this kind of sweet spot. It's the minimum there. It's the bond length. This was actually known as the Leonard-Jones 612 potential. And Leonard-Jones has an interesting story. He took his wife's name, well, at least he hyphenated. He's Levin. He was Leonard. Then he got married, and then he hyphenated his wife's name alongside him. Or I think he was Leonard, and one of them is his wife's name. So I think it's Jones is his wife's name, last name, I mean. So, besides his marital bliss, he did some good chemistry, and here is his potential. And the idea here is that on the far right end, you have the asymptote. The zero energy is the asymptote where you have two hydrogen atoms separated, infinitely separated. And as they approach, the potential energy goes down, and then it gets to a certain point where it has a maximum. And then if the atoms get any closer, they start to repel. So what is happening when they repel? It is the nuclei. The positive nuclei start to repel. There is a sweet spot where the atoms like to sit with each other. And with this discovery, it was thought that, oh, bonding is when electron clouds overlap. And with that came the idea of hybridization. So you overlap bonds, and for hydrogen sulfide, for instance, you would have the p orbitals overlapping with the s orbitals. But with this in mind, the bond length should be 90 degrees because of the p orbitals. But what happens instead is that you get hybridization, where the s and the p orbitals hybridize, and they form a new shape. And this is the 4sp3 hybridized orbitals. And the shape of that is then a tetrahedron. So the electronic geometry that is tetrahedron. So that's why when I said there's four things around an atom is going to have a tetrahedral geometry. And here is then methane. You have the 4sp3 hybridized orbitals, and they overlap with the hydrogen's 1s orbitals here, and that's how they bond. At least is the thinking with this. It's, spoiler alert, it's wrong, but as we turn out though, the geometry almost always matches. Using molecular orbital theory, it will almost always match the same thing with VSEPR, with a few notable exceptions and a few notable properties. So what about a double bond? So double bonds work via the sp2 hybridization. So this is the planar geometry. So instead of all three, just two. You have the s and the two of the two p's form a hybridized orbital, and it forms kind of like a clover leaf. Of course, if you can see this, there's going to be the positive and negative. This is the signs of the wave functions, respectively. That's a positive sign. There. Okay, so forms the new wave functions, and then you have something like formaldehyde. So formaldehyde here is going to have 3sp, 3 hybridized orbitals, and oxygen actually in this case is going to have 3sp2s as well. I'm sorry, 3sp2s. Both of them have 2sp2s and 3sp2s. And then what happens is you have the p orbitals above and below. Now they can overlap here, and that's known as a pi bond. So we have two different types of bonding. We have a sigma bond. A sigma bond means that the bonding is parallel to the nuclear axis. So like imagine I have my arm and I'm holding a book and I'm leaving the book away from my body. If you look at, like, if you compare the body, it was my heart to my book that I'm holding out. My arm is then the bond along the internuclear axis. That's a sigma bond. A pi bond is above and below that axis, so the bonding actually does not occur along the internuclear axis. It occurs above and below it, and that's the pi bond. Okay, and what is the consequence of a double bond? One of them is free rotation. So something like here, you have 1,2-dichloroethane. The molecule is free to move. That single bond, it's really easy to rotate among that. The single bond is pretty easy. It's a sigma bond. It just kind of flops around. A pi bond, however, a double bond, in order to rotate that, you have to break the pi bond. So because of that, it fixes the geometry of the molecule more. So here's a trans. I talked about trans before. This one is trans. Trans 1,2-dichloroethene. And, oh, I'm sorry, that's cis on the top. I'm sorry, bigger pardon, that's cis. So there is no free rotation there, and they're stuck. So that's the reason why you have both cis and trans with a double bond. And I kind of emphasized that a little bit more also with the Lewis structures there. So double bonds do not have free rotation as easily, although in a rod or cone we have the molecule cis-retinal. So this 1,1 cis-retinal, or it's 11, I'm sorry, 11 cis-retinal, the photon will change the shape of that. It'll excite it. And that is in part how our eyes work. Okay, so here's a summary of things. If it's a linear geometry, linear electron geometry, there's going to be sp hybridization. And not included, we have an s plus a p makes two sp hybridized orbitals. For trigonal planar geometry, it's sp2 hybridization. For tetrahedral electronic geometry, sp3. Bipyramidal, sp3d, and octahedral, sp3d2. So it forms those. And let's talk about the hybridization. So what is it? I can't read this. Use valence theory to write hybridization and bonding scheme for ethylene. So here is ethylene. Ethylene is this molecule, H. And ethylene is an interesting molecule. It smells like rotten bananas. So like if you ever, or like rotten fruit. If you ever smell fruit that as it's ripening, it's kind of rotten. What you're smelling is ethylene. It has a banana smell to my nose. And ethylene is also a byproduct of petroleum, and we've used it to make the most common plastic known as polyethylene, many ethylenes. So polyethylene is everywhere. But anyways, polyethylene is interesting for plants and for fruit ripenings because it's autocatalytic. A catalyst is something that increases the rate of chemical reaction, and ripening fruit releases ethylene, which makes fruit ripen more quickly, which releases more ethylene. That's, maybe you've heard this saying, a bad apple spoils the whole bunch, because adding ripened, like having a bad apple and a big thing of apples could cause the other apples to rot. So that's where that saying came from. Okay, so how does this work? So the ethylene molecule has it's planar, and that means it's sp2 hybridized, and along the carbon and hydrogen, each of those four bonds, those are sigma bonds, and carbon's going to have a sigma bond, but it's also going to have a pi bond. So it's going to have a pi bond above and below with that, and it's shown here in this picture as well. So we have four sigma bonds with the hydrogens, a sigma bond between the carbons, and then a pi bond between the carbons as well. And generally speaking, when you have a single bond, it's a sigma bond. If you have a double bond, it's 1 sigma, 1 pi. A triple bond is 1 sigma and 2 pi. So let's see if you're following. What is the hybridization of sulfur and SF6? So there are 6 things, and it is sp3d2 right there. And nitrogen, diatomic nitrogen, has how many pi bonds? So nitrogen has a triple bond. That means it has 1 sigma and 2 pi. So the answer is C, 2 pi. And how does the geometry work on this? So you would predict something like this. So nitrogen triple bond, you would think, okay, it looks kind of like a clover leaf because you have the p orbitals such like that. You would have the, so meaning along the plane. So let me draw this again. You have nitrogen, nitrogen, and then it's going to have the, it's going to be sp hybridized. So you have the lone pair and one of the SPs, and then you have a sigma bond across here. So then you're going to have a one of the P overlaps are going to be here along this plane, and then you're going to have another one along this plane. So you would expect it to look kind of like a clover leaf, but if you actually do the calculations and look at it, it actually tends to be more cylindrical. So it looks, the molecule looks more like a Tylenol than it does like a pill, like a Tylenol capsule pill, than a four-leaf clover thing. Because among other things, this theory is not entirely correct, but we will learn about the correct theory in the next lecture.